Hello everyone, I am Mahmudur Rahman Harry presenting on behalf of my group members Fawaz Mahmood and Pramita Singha. We worked on two empirical projects, the time complexity of binary search and connectivity in direct followership graphs. Binary search is a fast searching algorithm which works on sorted array. It repeatedly divides the search interval in half. The theoretical time complexity is 0. Our objective is to verify this complexity empirically. We tested array size of 10,000 up to 50,000. For each size, we ran 10,000 random search queries, measured average execution time and compared results with a logarithmic trendline. The average search time was almost constant, around 0.005 milliseconds across all sites. This confirmed binary search follows logarithmic time complexity and is efficient for large datasets. Next, we analyze directed followership graphs, where users are nodes and follows are directed edges. We generated graphs with 500 to 2500 nodes. Edges were added randomly with probability 0.01 with no self loops. For each graph, we computed degrees, checked constantly, and identified WCC and SCC. For all cases, graph was weakly connected. At 500 node, there were 7 SCCs. But for 1000 node and above, the graph was strongly connected. So with probability 0.01, the directed followership graphs are always weakly connected. And as the size increases, they also become strongly connected. In summary, binary search was confirmed to be logarithmic in practice. Directed graphs with random edges remain weakly connected and large one become strongly connected. These results validate our theoretical expressions. Here we can see the result of our binary search experiment. The table shows average search time of arrays from 10,000 to 5,000 elements. Notice how all the values stay around 0.005 milliseconds. This indicates the growth rate is extremely slow and almost flat. And if you look at the plot, the experimental points align very closely with the theoretical logarithmic curve. That's why we can confidently say binary search behaves as 0 in practice. Now let's move to the followership graph result. The table shows the number of edges in degrees, out degrees and connectivity results for different network size. At 500 node, the graph has 7 strongly connected components, meaning direction creates separate groups. But from 1000 nodes onward, the SCC count drops to 1, showing that the graph becomes fully strongly connected. The visual confirms the trend. Larger network with P equal to 0.01 quickly becomes strongly connected while staying weakly connected in all cases. In the code, we generate random array, sort them and then run binary search for 1000 random queries. We measure execution time using Python and take the average. This is what produced the table and plot we just saw. For the graph, we use Python with the NetworkX library. We generate random directed graph with a probability of 0.01 per edge. Then we calculate in degree and out degree. Then we finally used built-in functions to find weakly and strongly connected components. The output gave us the value in the table and we plotted them for visualization. These results validate our theoretical expressions. Thank you.